Hi, my name is Peter Laud, and today I'm going to present you the work that we have performed here with my colleagues Alisa and Martin about the framework of metrics for differential privacy stemming from local sensitivity. So, a general data release problem is that we have a database, we run some queries on it, we get some output, the output is made visible to somebody. This somebody could be an attacker, so he might try to deduce something about the content of the database from the output that it sees. So in order for the output to be useful, this cannot be completely prevented, but we could reduce the effect by adding some noise to the output, so that when the attacker sees the noised output, he can deduce less about the database. The amount of the noise, it can be adjusted, and we should find a good distribution to pick the noise from and a good magnitude for this noise. Indeed, so if the two databases are very different, then it might be impossible to hide from the adversary whether we use the first database or the second database, or if we manage to hide it, then just the result might be useless. But there may be chances to hide small changes. And when talking about changes and the sizes of those, well, we need to have some measure of changes, and typically this size of changes can be expressed through a metric. So we have a set X, we have an information release mechanism F, which could be a SQL workflow, and it gives you a value from a set Y, and X is a metric space, so there is a metric defined on it. So, and if X is a set of databases, then a typical distance on databases is the number of rows in all tables that we add or remove or change. Adding or removing one row means distance 1. As we discussed about noise, so F really has to add noise, so F does not always return the same result when applied to the same database. So F is really a probabilistic function. So we let this d of y denote the set of all probability distributions over a set y, and F transforms a database into a probability distribution over a set y. And then we have this definition of differential privacy. So we say that F is epsilon differentially private if for two different databases X and X prime, the probability of getting a certain result does not change too much. So the change is bounded above by the distance between X and X prime, and the bound is multiplicative. So this is the standard definition of differential privacy. And going forward with the example of SQL workflows, let's have this example here that there are a number of ships on the sea, and there are also a number of islands in the sea, and for some reason we need one ship to reach some island as quickly as possible. And if we have recorded the data about the ships in the table and data about islands in a different table, we would ask how fast a ship can arrive at an island, and this could be an SQL query. And when discussing what we may want to hide here, I mean, we have islands, and probably islands have names, the islands have locations, both of them can be considered public. The ships, I mean, their names could also be considered as public, because I mean they are just identifiers of the ships. On the other hand, we consider the locations of the ships to be private. I mean, the ships can move around on the sea, so the locations are definitely private. Okay, maximum speed of the ship does not change so often than the location of the ship. So really, depending on the application, it could be either private or public. So here the picture is really an instance of the database, and well, when we could change one row in this database, one row in the table of ships, and then this database could look something like this. So the one ship has changed location. I mean, still we can tell that probably the minimum time of a ship reaching an island did not change because of that. On the other hand, I mean, this is also change in a single row, and this most probably changed the outcome of a query. So we really see that not all changes in a single row are the same. So a row can change a little, it can change a lot. It really makes sense to treat such changes differently, because otherwise the privacy mechanism that we choose might not be the most appropriate one. Either we choose a mechanism which will be appropriate to hide the small change, and then this mechanism is too powerful and most probably too noisy for the large change. Or vice versa, if it's adequate for the large change, then it may be not powerful enough for hiding the small changes. Indeed, this distance on databases can be defined in various ways, and if we have several different private columns in a table, then there are actually trade-offs to be made. For example, if both the location and the speed are private, then how do we weigh a change in the location versus a change in speed? And indeed, so this distance is something that the data owner or privacy policy officer should determine. And so the distance is indeed a part of the privacy policy itself. Let us now move forward to determining how large the noise should be. We know there are a number of ways to compute an appropriate magnitude of noise for differential privacy, and they all have to do with the sensitivity of the computation, or in this case the sensitivity of the SQL workflow. We could use the global sensitivity of the workflow and deduce the noise magnitude from it in order to get differential privacy with a particular value of epsilon. Or there is also local sensitivity, which also takes into account the current contents of the database, so that for databases where a small change may mean a large change in the result, we would add more noise, and when the database content is such that a small change cannot change the result of the workflow much, then less noise would be sufficient to achieve differential privacy. The global sensitivity of a function is defined like this. So indeed, we have a set X, which is a metric space, so there is a metric on it, and we have a function into another set, which is again a metric space. And in the simplest setting, the set Y is just the set of real numbers, and the distance between real numbers is just a difference. And we define that the function f is C sensitive for the real number of C if the change in the function values cannot be more than C times the change in the values of arguments. And this applies for any 2 points in the domain of f. So to reword this, we say that the global sensitivity of f is a supremum of the following formula, where we divide the change in function values with a change in arguments. And we know that there is this Laplace mechanism for making a finitely sensitive function differentially private. And this works by post-composing the function with a noise addition. So we here have this noise addition function, which samples a value from the Laplace distribution with parameter sigma and adds it to the given value. And we know this mechanism of making f differentially private, so we post-compose it with a noise, where this argument sigma is proportional to the global sensitivity of f and inversely proportional to epsilon. Of course, the global sensitivity is a one-size-fits-all mechanism, and this is its shortcoming. I mean, the function f might change rapidly in some part of its domain, like here. And here, the addition of large amounts of noise would be justified, but in some other region, it might change much more slowly, so that less noise would be sufficient. To remedy this, local sensitivity of the function f was proposed, and here the local sensitivity is now argument of an element of the set x. Indeed, so for each point x, there is a different value for the local sensitivity. And we could use local sensitivity to scale the amount of noise that we add. But now we also know that the amount of noise itself may leak something about f. So if the local sensitivity itself would change sufficiently slowly, then we could use it to scale the noise. But in general, we could look at upper bounds of local sensitivity, and such upper bounds that have global sensitivity at most beta, where beta is another numeric parameter. And again, there are ways to use local sensitivity to make functions differentially private. And again, we do it by post-composing the function with noise, but now the noise has to be selected from a different distribution. It is the generalized Cauchy distribution. And again, there is a theorem which tells us how much noise should be selected. And now this parameter of the noise, we see it also depends on the value of x. When we look at the expression of local sensitivity and the inequality that it satisfies, we see it is actually rather similar to the derivative of a function. In particular, when the domain of f basically just has a single dimension, so that the domain x is again the set of real numbers, then the derivative of f with respect to the variable x is defined like this. And when we consider the fraction between the distances of function values and the distances of arguments, then the value of this fraction is actually achieved by this function at a certain point z, which is between x and x prime. And if we consider not just the derivative of f, but some beta smooth upper bounds of this derivative, then this derivative value at z is actually close to the derivative value at x prime, where the closeness actually depends on the value of beta. There is a reason why we want the sensitivity of the queries to be defined in terms of derivatives, because when we then start computing these sensitivities or the upper bounds, then we could use all the methods of calculus, so there is a rich toolbox for them literally developed over the century. If we come back to our example, we have ships parameters and we want to define derivatives for these SQL workflows over this table of ships and table of islands. So we quite naturally end up with Banach spaces. So the Banach space is a vector space which is equipped with norms and which is complete. And we think of our set of possible databases as a Banach space. Recall that in our example, the number of rows in each table has actually been fixed, so that this Banach space that we have does have a well-defined dimension. And as a query, we consider an SQL workflow that computes a number, so the query really is a mapping from this Banach space to the set of real numbers. As we said, the local sensitivity is rather similar to derivative, or actually to the size of the derivative. So we define a version of local sensitivity which we call derivative sensitivity, and it is actually defined in a very simple way. The derivative sensitivity of a query f at a certain point db, where db is an element of this Banach space B, well, it is the operator norm of the Frechet derivative of f at this point db. Now, in this expression, there are several words which need some further explanation. Let us first start with the derivative. So normally we define derivatives for functions that take real numbers and also return real numbers, and the derivative of this function at some point x is again a real number, and this real number has the following property. Let us say that we just change the argument of g a little. So we add some small delta to x. In this case, this g at the point x plus delta is more or less g at the point of x plus a change which is proportional to delta, where the coefficient is equal to the derivative of g at x. And the error here is negligible in the size of delta. Similarly, the derivative of a mapping from a Banach space to real numbers at a certain point db is, well, perhaps not so similarly. It is a linear operator from the same Banach space to real numbers. Still, it is rather similar if we reword the usual derivative of a little bit. So instead of considering this g prime of x as a real number, we would think of this derivative again as a linear mapping from real numbers to real numbers. And well, the only linear mappings from real numbers to real numbers are those that multiply its argument with a constant. So this constant would be this g prime of x. And then this approximate equality can be rephrased as follows, that this changes this d of g at the point x at the change delta. And indeed the Frechet derivative is similarly defined, so now this linear operator must work like this. But again, when we change this argument a little, but now delta is also a multidimensional change. Delta is again an element of the Banach space, so that when we apply the Frechet derivative to delta, well, we almost get f at point db plus delta, where again error is negligible in the size of delta. The other part, operator norm, just states how much it could increase the length of its argument. And as we show in the paper, the derivative sensitivity can indeed be used to achieve differential privacy, again by post-composing with the addition of noise, and again this noise can be sampled from the generalized Cauchy distribution. Instead of generalized Cauchy distribution, we could also consider a Laplace distribution, but then we are not going to get epsilon differential privacy, but we are only going to get epsilon delta differential privacy. How do we compute the derivative sensitivity of a mapping, which might be an SQL workflow? Now, this depends a lot on the norm that we use on the Banach space. In the easiest case, let's say we have an n-dimensional space and we have an LP norm on it, and in this case, the derivative sensitivity of f at a point x in this space is just given by the partial derivatives of f at this point, where these values of partial derivatives are again combined by a different norm. We also have a combinator property. So let's say we have a Banach space, which is really a Cartesian product of two Banach spaces, and the norm on this Banach space is also a combination of the norms on these component spaces with an LP norm. And in this case, we can again compute the derivative sensitivity of f as a combination of the derivative sensitivity of f restricted to the first component and the derivative sensitivity of f restricted to the second component. In general, we are interested in Banach spaces where the norms are composed from the norms of smaller things. So in general, we have attributes, and the norm of the attributes is just the value of this attribute. The norm of rows we construct as an LP combination of the norms of attributes, or we could also define a norm for a part of a row and a different norm for the different part of a row, and then we could compose them again using some LP construction. And the norm for the whole tables, it somehow comes from the norm of rows, and again it could be defined using different LP norms. So the typical definition where change in one row means a unit change in the norm, this would correspond to L1 norm for the table. And finally, again, for the database, it's the same thing. We get the norms of the tables and we somehow combine them. It could again be L1 norm, or it could be some other norm. And all these different ways of defining a norm can be meaningful. These different norms correspond to different privacy policies. For each query, there is some norm with respect to which one the sensitivity of this query is natural to compute. In general, let's say, well, we have some query, for example, compute the exponent of x. In this case, the natural norm here would be just the magnitude of x, so that the natural derivative sensitivity would be the derivative of e to the power of x. So this natural norm for a query is determined by the query, which is determined by the analyst, but the privacy policy for the database, it's determined by the data owner or by some policy officer. He might have specified a different norm. So how do we reconcile this? We are able to compute the sensitivity of a query with respect to one norm, but we are really interested in the sensitivity with respect to a different norm. Consider still the same query here, computing the exponent of x, and then consider also possible database norms, some examples of which are given in the left column of the table. What we are now going to do is, well, we are going to upper bound one norm with a different norm. So the one norm that we are going to upper bound is this database norm, and the different norm is now related to this natural norm of this query. We can actually use this derivative with respect to query norm to upper bound the derivative with respect to the database norm, and we can use the derivative with respect to the query norm to compute the magnitude of the noise. Our approach is applicable to SQL workflows and SQL queries that have database joins, and indeed also to joins that use the same table multiple times. In this case, we can think of just having multiple copies of the table, so we compute the sensitivity for each table separately, and we can combine all copies of a row using the infinity norm. Again, this is explained in more detail in the paper. Finally, let us consider the following. We have stated that this database norm, which gives us the distance, is a part of our privacy policy. On the other hand, of course, the epsilon of the differential privacy is also part of the privacy policy. And we see that there is an obvious degree of freedom. Namely, if we scale the distance by some factor, let's say some alpha, and at the same time we also scale epsilon by the inverse of alpha, then we actually haven't done anything. If we have fixed the distance, or let's say if we are using some very canonical distance. But if the distance is chosen as part of the privacy policy, then really you choose the distance and epsilon both at the same time. To conclude, we have shown that there is a rich set of defining distances over sets of databases, and they all can be meaningful when defining privacy policies. We have also shown that the local sensitivity and the derivative are really very similar, and the mathematical tools of computing the derivatives can be used in determining the amount of noise one has to add in order to get differential privacy at a certain level.